The United Kingdom pours roughly £7 billion of public investment into its railway infrastructure every single year. You can see the physical scale of this capital expenditure in massive earthworks, new road bridges, and sprawling track renewals. Yet, despite that financial weight, the operational reality consistently lags. With average punctuality hovering around 74%, the network underperforms relative to heavily invested European counterparts like the Swiss Federal Railways. Pinpointing exactly where to spend the next £1 billion presents a severe analytical problem. The UK rail network is a live, highly fragmented mix of public infrastructure and private operations. You cannot isolate a single passenger route in a vacuum to conduct a controlled experiment. Without experimental control, policymakers are forced to rely on competing financial models and high-level macroeconomic projections. This makes it difficult to isolate exactly which physical upgrade actually drives measurable transport efficiency on the ground. To bypass the limitations of physical hardware, researcher Mohammed Akhavat designed a different approach. Instead of measuring the tracks themselves, he captured the aggregate, structured consensus of 100 top-tier rail sector experts, the engineers, planners, and managers who actually run the network. Investing billions into capital projects without an empirical hierarchy of what works risks misallocating resources. To optimize the railway, we must first mathematically validate the professional instincts of the people operating it. The engineering sector is traditionally skeptical of subjective survey data. Perception is vulnerable to local bias, to institutional allegiance, and to anecdotal memory. To strip away that bias and noise, Akhavat constructed a strict post-positivist methodological pipeline. It moves linearly from questionnaire design through reliability validation and bivariate correlation into categorical testing and finally to a definitive conclusion. This pipeline subjects qualitative human perception to the exact same rigorous mathematical stress testing that physical concrete and steel undergo in a laboratory. By stepping linearly through this statistical pipeline, we can observe the mechanical process of transforming subjective professional perception into rigorous policy-grade data. The first step required a specific sample. Akhavat surveyed exactly 100 active professionals divided across 5 distinct categories: infrastructure engineers, policy advisors, network rail managers, local planners, and academic researchers, ensuring comprehensive institutional coverage. The core of the instrument was Section 2 of the questionnaire. This section was engineered specifically to test the relationship between physical infrastructure dimensions and passenger efficiency outcomes. Rather than a standard 5-point scale, respondents were restricted to a 7-point Likert scale. This design prevents respondents from clustering in the middle and provides the discriminatory power required for precise statistical testing. The researchers also enforced a critical subcomponent averaging rule on every respondent. If asked about track condition, an engineer couldn't grade rails a 5, sleepers a 4, and ballast a 3. They were required to mentally calculate and submit a single, unified average score that represented the entire track assembly. Forcing this specific averaging eliminates hyper-localized technical biases. It structures the qualitative data into a continuous numerical format, unlocking the ability to run powerful parametric statistical tools in the next phase of the pipeline. In quantitative research, there is a strict sequential rule. Before analyzing a single answer for meaning, you must prove the test itself is structurally sound. This concept is called construct validity.
You have to prove internal consistency, verifying that the distinct questions in the survey are all pulling in the same logical direction. This formula represents Cronbach's alpha. As covariance increases, it pushes the coefficient closer to a perfect 1.0. This tests if the survey questions measure the same latent construct. The calculation returned 0.831. In statistics, 0.831 passes the threshold to be classified as good internal consistency. Akhavat has mathematically proven his instrument is reliable, producing a verified dataset ready for inferential analysis. Step 3 of the pipeline moves into inferential statistics. This is where we isolate exactly which infrastructure dimensions exert the highest influence on actual network efficiency. This is a Pearson correlation matrix, using Pearson's R to establish the strength of associations between variables. Track condition and station infrastructure show only moderate associations. But signaling modernization emerges as the absolute strongest driver of capacity and on-time performance, correlating at 0.82. Returning to the matrix, electrification infrastructure shows an overwhelming 0.81 correlation with carbon reduction. The double asterisks sitting next to these R values denote a high degree of statistical certainty. We often associate railway improvement with visible concrete projects, but data proves the digital backbone, the European train control system, dictates actual throughput of the physical hardware. Those asterisks indicate a p-value of less than 0.01. This means there is less than a 1% probability that these strong correlations occurred by random chance within the sample. The results provide a clear hierarchy. Invisible operational upgrades like ETCS signaling and overhead wires mathematically dominate visible station improvements in driving network efficiency. Identifying the optimal infrastructure solves the engineering problem, but it exposes a structural one. Do the different institutional factions running the railway actually agree on how to implement it? To find out, we use a chi-square test of independence to determine if survey responses differ based on professional category. When evaluating concerns over the pace of the digital rail rollout, a p-value of 0.015 confirms a statistically significant divergence regarding delivery delays. A p-value only proves that a divide exists. It doesn't measure its severity. For that, we require a secondary test called Kramer's V to measure the magnitude of that divergence. The Kramer's V value returned a medium effect size, validating theories of institutional information asymmetry within complex infrastructure projects. The finding is specific. Frontline engineers and operational managers possess a far more acute calibration of delivery risks than policymakers responsible for network funding. Looking at the complete journey, the post-positivist methodology has successfully filtered out institutional bias, anecdotal evidence, and fragmented reporting. The Pearson matrix translates into a 5-tier priority list for UK rail investment. It builds from station quality to track condition, through sustained investment, up to electrification, and peaks at signaling modernization. This hierarchy anchors directly to the statistical outputs. The policy implication is clear. To achieve rapid capacity gains and carbon efficiency, the Department for Transport must prioritize digital control and overhead power over visible concrete. By systematically quantifying the variables that drive on-time performance and capacity utilization, the research moves past broad macroeconomic modeling into granular, evidence-based engineering. Subjective professional perception, when subjected to strict internal reliability tests and categorical analysis, results in a mathematically validated strategy for national infrastructure success.